So let me quickly introduce today's webinar. The speaker is Arnoldo Frigessi. He's a professor of medical statistics at the University of Oslo. He also is leader of a big state-financed project on applications of statistics in society called Big Insight. And he's also quite into the statistical analysis and modeling of COVID and virus spread in Norway, as you can see from this slide. And he's also a very old and dear friend of mine, so I have the pleasure of giving him the screen now, not the floor, but the screen. So Arnoldo will present his talk about COVID in Norway. Prego, Arnoldo.
Thank you very much, Jampi. Very nice that you give me the opportunity to talk about the recent work we've been doing in Oslo. It's really work in progress in many directions, and I hope that you will have some good advices. So I'll start with let's see. Yes, I'd start by mentioning immediately the good friends and collaborators who've been working on the material that I'm going to present to you today. And this is the so-called modeling group of the National Institute of Public Health, which is directed by Birgitte Freiesleben de Blasio. And then it's Gunnar Rø, Alfonso Palomares, Anja Kristoffersen, Francesco Di Ruscio, Solveig Engebretsen, Geir Storvik, and Kent Engø-Monsen. Very important collaborators. My plan today is to give you first a little bit the context of the work that we did in the modeling group. The context is important because it says something on what was the playing ground we have been moving in the last 4 months. I'll tell you something about the data. The model, then we call it the change point model. Inference, which is based on ABC. I'll show you some results, and at the end I'll use a little bit time on a second model for a time-varying reproduction number, because there are difficulties there, and I'd like to discuss a little bit the difficulties before I come to some conclusions. So the context. In Norway, the decisions are taken by these people here. It's the Prime Minister, the Ministry of Health in the middle, and then it's the Norwegian Institute of Public Health on the left, and on the right, Helsedirektoratet. And their role is quite precise. The Norwegian Institute of Public Health is advising, the government is deciding, and the Helsedirektoratet is implementing. And on the 12th of March, the government decided a semi-lockdown for Norway. It was not as serious as the one in Italy or later in other countries. And this decision was taken by these people. Here you see the director of the National Institute of Public Health, based on the situation we had at that time. So on March 10th in Norway, there were 277 lab-confirmed cases, of which 183 were imported from Austria and Italy. They've been skiing in the Alps, and they infected 81 further in Norway when coming back. 3 days afterwards, the numbers were much higher, 750 cases, 500 imported, and 156 in Norway, and the first one was dead. So it went very rapidly. And the government made decision also based on the plots and graphs that we in the modeling group produced at that very early time. It's almost embarrassing to see what we produced at that time with very little data and very little time, but it was important. And it has been a pleasure and exciting to be part of this. The government decided to have a strategy that was very clear. Keep control of the spread of the virus. And what does it mean to keep control? It means to maintain the number of patients in a number that is manageable by the Norwegian health system. But recognizing that the number of patients will go up and down, and it will vary in regions. And we received, the modeling group received a very clear, let's see now if this is working like this, a very clear request. We were asked to produce a prediction of the number of COVID patients, in particularly the number of patients that require invasive mechanical ventilation for the next 3 weeks and for the next year. And then we were also asked to estimate prevalence and reproduction numbers to understand the situation, the nowcast. And all this at national level and at regional level. The data that are available in everywhere, right, in all the countries are these ones, right? The number of people tested and who have been found positive, the number of COVID patients in hospital, the number of COVID patients that need respiratory assistance in ICUs, the number of new people admitted to hospital, new patients, and the number of deaths. And all these data sets have difficulties and powers, right? The number of tested is changing all the time. The testing capacity in Norway has been moving up slowly, but systematically. More important is that the criteria for who should be tested have changed all the time. And this makes these data very difficult to use. The number of hospital is good data, but you need a good model of how long people stay in hospital. And the same for ICU. The number of new admissions to hospital is also interesting data. They are more irregular and noisy, less smooth than the number of patients in hospital every day. And the number of deaths is available, but you need a good model of death. And people die in hospitals and people die outside hospital. 60% in Norway die outside hospital. And all these data are available at municipal level. An important point to take decisions of which data to use is also to understand the delay that these data inheritably have. Delay means that they say something on the infectiousness days before. So the number of tested or the percentage of positive who've been tested maybe has a delay of 2-3 days. This is a reporting delay and some other delays. The number of people, the prevalence in hospital has a delay of about 2 weeks, ICU a little bit longer, and the number of deaths even longer. So looking to this situation, we decided to work on 2 types of data mainly, which is the number of patients, COVID-19 patients in hospital, and the number of newly admitted in hospital every day. The other data source that we have has been provided by Telenor. It's a mobile phone company in Norway that has about half of the market share. The idea was to using mobility of mobile phones as a surrogate for real-time mobility patterns of individuals. And the data that we receive every day is as follows. So there are 356 municipalities in Norway, Oslo is one, and the data count the total number of movements from one municipality to another. And this happens every 6 hours, so 4 data points per day. However, the movements are monitored in a special way. So during these 6 hours, let's say between 6 and 12, only the first 2 hours between 6 and 8, the SIM cards are tracked, and what counts is the last location observed at the end of these 2 hours. Why only 2 hours out of 6? This has essentially to do with dimension of the data set and feasibility to produce these matrices every day regularly. So we have only a partial control of the movements. We also have something that has to do with privacy. So every count that is below 20 has been censored. There are many small municipalities in Norway where there are very few people that move from A to B, and these counts are censored. But we have this data every day since February 24, and we scale them up just by doubling them essentially to the whole population. Here you see a picture. These are the movements in the morning and then later in the afternoon. In Norway, Norway is a long country, so there are some movements that are by plane, and otherwise lots of commuting around Oslo that you see there as a black star down there. The data have been quite useful, the Telenor data. Here you see a plot of a time series of the total movements out from each municipality. These are the 20-something largest municipalities in Norway. The blue one is Oslo. So you see first of all, you see a weekly cycle with the weekends where movements drop. But apart from this, you see very clearly that at the day of the lockdown, which was on the 12th of March, there has been a collapse of movements out from Oslo to about a third or even less than a third. And during lockdown that lasted from the 12th of March until the 20th of April, you see that, I don't know if you see probably you don't see my pointer, right?
We do. You do.
Okay. So then you see here that the movements have been remained low, but started to go up slowly, regularly, about 2% per day. And continued also during the opening. So the opening was a slow opening where it started with some classes and the kindergartens and continued. So here you see it went up more or less with the same speed and continued. Here are the last days of activity in June, where activity was quite high, some vacation times here, and then recently a drop because of the July vacation in Norway. This is just to show you that we see the expected patterns that indicates that this data might be useful to understand how people move in the country. The regional meta-population model that we use has 3 layers. A simple population structure that tells us where the 5.5 million Norwegians are, in fact, where they were resident in January 2020 by data from the Central Statistical Office. Then there is a compartmental model of spread that I'll tell you about, and then there's the mobility data from Telenor that tells us how people move between municipalities. So the model is a very standard stochastic SEIR model. You have seen it, I'm sure, in many lectures and presentations. So I'll be fast here. You have the susceptibles, and some of them is then infected and becomes exposed. For sometimes the person is non-infectious and doesn't have symptoms, and then it can either become an infectious asymptomatic case before recovering, or it is an infectious symptomatic case, and in that case there is a pre-symptomatic phase that is recognized as being particularly problematic for COVID-19, where people don't have symptoms but are highly infectious. We have such a model for each of the 356 municipalities, and there are parameters that are in common for all the municipalities, many parameters. I'll come back to them. But there are some parameters that are special for every region. Not for every municipalities, but for every region, for every county. In Norway, there are 11 such counties. Oslo is one. You see a map down there. In the north, there's a big one, and so on. And for example, the probability of transmission, beta T is going to be different for every county, for every fylke, as they're called in Norway. It also depends on time, as I will tell you in a minute. We have a change point model for that. So here I'm back. So you can write down stochastic difference equations here, because we have these 6 hours intervals. We use 6 divided by 24 as our delta T. And these are the standard equations that you all know, that tell us how such a system behaves. And you see the assumptions on the stochastic assumptions. We have lots of parameters in such models. and many of them are not estimated, but learned from the literature and other studies. So, for example, there is time people are exposed and not infectious, lambda 1, a latent period, which we assume to be exponentially distributed with a mean of 3 days, while the time, the pre-symptomatic group is going to be exponential 2 days, and so on. And you see here the various assumptions. In particular, we assume that about 40% or 40% of the infected people remain asymptomatic, and 60% are in fact showing symptoms. The beta T here, the beta TF, it should be an F here, is the probability of transmission upon contact that is reduced for the asymptomatic subgroup by a factor that we currently assume to be 10%. And the pre-symptomatic is in fact increased by a factor 1.25. We assume that the population size remains constant in the municipality. So there's no emigration in and out. You can compute basic reproduction numbers that are the ones that are reported to the public by multiplying the beta T with the thing that is needed, and then there is the important part of the model dynamics. So I told you how the infection is behaving inside the municipalities, but let's look to how people now move. So first of all, each individual in the model has a residence. So I'm from Oslo and I remain from Oslo all the time, even if I move and travel somewhere else. And every day at times 0, 6, 12, and 18, individuals are moved using the Telenor mobility matrix of the previous 6 hours. So if it says that there are 364 people that move from Oslo to Bergen, then this happens at that start of the 6 hours. And then I am in Bergen for 6 hours and I mix randomly with the people that are in Bergen at that time, that are from Bergen and from all the other places that have moved there. An important choice is to decide who to send back in some sense. So imagine that we have now to implement the travel of people from municipality A to J. And we do it in the following way. First of all, we send back to J residents of J that are currently visiting I. So we favor a commuting component. So the first one that is sent back are the last one that arrived. And if there are many, we choose them at random. Sometimes we don't have enough because Telenor tells us that we have to send 500 people from Bergen to Oslo while only 300 just arrived there. So then we take the remaining one. They are visitors that are currently in I that come from J. And finally, I move residents of the commune where I am. So you see that these choices are difficult to justify in detail, right? But they favor commuting. They allow long travel, but they favor a preservation of the a returning to their own residence in some sense. Yes. If I write the matrix xijt is then the number of people who were in location I at the end of the 2 tracking hours, is only 2 tracking hours as of the previous interval, and then we're in location J at the end of the 2 tracking hours at interval T. So this is the data from Telenor. And XIIT is the one that don't move, right? So then one can write down this equation that says that if all movement would be recorded, then this equality would hold. It simply is a preservation of people, right? But this is not the case, because lots of movement escape the telenure tracking. And why does this happen? Well, this happens because, first of all, some phones are turned off or while moving. This happens, for example, on airplanes, but other occasions also, or simply are not properly connected, or they are exiting the telenure's net. So all these things can happen. So this equation one I showed you is not satisfied by the data. And if we just ignore this fact, then what can happen is that some municipalities will be depleted from people. And you can come in a situation where you have to move out 30 people from one municipality and nobody is living there anymore, because you have not preserved properly things. Now, this happens in particularly, it doesn't happen much, but it happens for smaller municipalities. And when we do 3 weeks prediction, this happens so little that we simply add the missing people that as immigrants. But if we do longer predictions, this is problematic. So, because these imbalances propagate, right? So in these cases, we have to regularize the matrices, and the way to regularize this here is to make sure that these matrices have row sums equal to column sums. You can see this just by putting by assuming certain stability in the system. And therefore, we are simply looking for the closest matrix Z to the data of telenure X that satisfies row columns equals row sums equal column sums. And we do this by quadratic programming with the linear constraints. And that's easy and goes fast. So we regularize the matrices before doing prediction. We use the real matrices during in the historical part in the past, but when we go forward, we do regularization. Then I have to tell you something about the hospitalization data. We have good hospitalization data. So only people that are symptomatically infected are sent to hospital. And this happens according to their age. And we are using the findings from Imperial College, from the Salje and other papers in recently, and scale them to the demography of every individual municipality. And we also correct for the fact that in Norway, there is a certain percentage of people that are living in elderly home that is different from other countries. So if here you see, for example, the probability of being sent to hospital, if I make a national average now, the probability becomes higher for elderly people, and it's when you are in my interval between 60 and 69, it's 7%. The Norwegian registry data are quite good, and they allow us to look carefully on what is the history of a patient with COVID in the health system. So here you see what we estimate. We repeat these fits and estimate every second week. These ones are based on 1,300 patients, and they say, for example, that the time between onset of symptoms and hospitalization has a mean of 9 days and can be nicely modeled with a negative binomial. The probability of needing intensive care unit is about 15% in Norway. The others don't need it, and the others remain in the hospital ward for about a mean of 6 days, negative binomial again, before they're discharged. If they go in the ICU, then there is about 3 days that are spent in the ward before entering the ICU, geometric distribution, negative binomial with 16 days of mean in the ICU, and then about another 8 days negative binomial back to the standard ward system. So you see that for those who need respiratory treatment, the time in hospital has a mean of almost a month in Norway. So these are our estimated distributions that are used to send people into hospital in the simulation, right? Now I tell you something about the change point that we are assuming. And this is to do with how the interventions have been introduced and lifted in Norway. So here you see a graph where you see with red arrows pointing down the time point where interventions were introduced. Now, so far, all the interventions have been nationwide. There were no interventions that were only restricted to some regions, but this will come in the plans of the Norwegian government if needed in the future. And then you see with green arrows going up is when they were lifted. And you see that there are two main points when things are changing, and we use them to guide us in fixing the change points. So one change point is now fixed to 16th of March and the other one of 20th of March. It means that we have for every county 3 betas, one acting before the 16th of March, one between the 16th of March and the 20th of April, and one afterwards. We have now introduced, in fact, a third change point on the 11th of May, but I will not show you the results in that case. We do some estimation or calibration on the choice of the change point. For example, we choose the 16th of March by comparing fits by putting the change point between the 9th and the 18th of March and so on. We are going to be Bayesian, so we put priors on parameters that we estimate, and you see down there quite informative priors that come from international studies mainly. Another important point I have to make is the seeding of the model. So Norway had this particularly issue that many cases were imported in particular in the beginning of the epidemics. You see here in dark red is in these columns is the number of people with COVID-19 that were confirmed in Norway, but were infected not in Norway. And what we do is that we take these imported cases, because we know where they have their residence, we put them in the municipality where they are resident. Or if this is not known, we put them in the place where they have been tested. And then we also recognize that there are imported cases that have not been detected, and therefore we introduce an unknown amplification factor, we call it like this, that represents essentially the factor that is for every detected case, how many undetected have been walking around. And we assume that it has a Poisson distribution with a mean that we have to estimate, and the prior is, as you see, given down there. So we're going to estimate the amplification factor that is the same for all Norway. Inference is then for the 34 parameters that are in the game. So it's 3 transmission parameters for the 11 countries plus the amplification factors. And in what I show you now, we use daily hospital prevalence in each of the COVID-19 treating hospitals. So here you see, for example, the hospitals in Oslo. It's about 4 or 5 hospitals. This is put together. This is time from the beginning of March until very recently, and you see how the numbers have been evolving. This is the prevalence. It was at most 150 people in hospital, patients in hospital. If I go up in the north, Troms and Finnmark, this is in the top of Norway, the numbers are much smaller. This is 12. So it's because there's less population there, and also the virus has been less spreading less. So these are the data that we're going to use. And the method that we're using is an ABC method. It's a sequential Monte Carlo ABC methods that combines particle filters with ABC. The idea is that it's an iterative method. You make several rounds and you improve your parameters from round to round. And I'll tell you in a minute roughly how this works. It's inspired by work of Sisson and Fan and Tanaka and Brooks Pollock and Gareth Roberts and Matt Keeling several years ago. And the idea is the following, right? That you, first of all, you you start with sampling your 34 parameters from the priors, and you compute and you you run the model and you produce hospitalizations, and you compute the mean square distance between the predicted number in hospitals and the real data. And you take the 1,000 sets that are best out of the, let's say, 10,000 that you start with. And then you start to iterate the following thing. You sample the set of parameters theta from the ones that you have accepted in the previous round using important weights. I'll say in a minute which one we're using. Then we propose new parameters theta prime by sampling from a multivariate normal distribution that is centered in these thetas that we have, the nice thetas that we have from the previous round, and then has an empirical covariance matrix that is estimated from the parameters of the previous round. So this is a 34 by 34 matrix that shows that many of these parameters are strongly correlated. So this is important to keep. And then we again run these theta prime models, these models with theta prime, and we keep the theta primes which have a mean square distance between prediction and true data, which is below the 80% quantile of the error in the previous round. And the important weights are given here. They are sorry, the notation is slightly different. I just copied and pasted from a paper. It's essentially the prior divided by a weighted Gaussian kernel model. We do this and at every round we continue until we have 1,000 parameters that are good, and then we continue. So also at the end we end up with 1,034 dimensional sets of parameters, and we use this to compute point estimates and credibility bounds and predictions. The algorithm, as you see, we don't know how much time it takes to produce these 1,000 parameters all the time. So we have been occasionally waiting for more than we thought. I'll come back to that. So let's see how much time we have. Another 10 minutes, Jumpy, right? Something like that? Yes. So I'll show you results that are based on data until May 31st. And as I was mentioning, here it is already. So these runs have been done on a dedicated server with 200 nodes and lots of parallel simulations. And when we do it like this, it takes about 12 hours, more than a night. So it's clear that we probably can't scale it very much more than what we're doing now. When we will start to introduce more and more change points, we will not have 3 parameters for every filter, but maybe 8 in a year. And we will have to think what to do with that, because we still need to take the data of today, they're given at 12 o'clock, and produce a prediction at least tomorrow morning, not much after that. Here you see the estimated reproduction numbers, the three reproduction numbers for the 11 counties in Norway. You see that the first one was higher in the beginning. It was pre-lockdown, and it was between 2 and 3. For some region, even higher than 3. And then the 2 others after lockdown and after reopening are much smaller. So if we look to Oslo, for example, it went down to 0.73. 95% credibility intervals are given here, and currently it's between 0.3 and 1.2 in the 31st of May, and this is a credibility interval that is interesting. There is a probability of being larger than 1 still. If we go to another county that has a lot of people, Viken is the most populated area, it's around Oslo. You see again a credibility interval that is broad. It's broad, but interesting in any case. There are areas like Troms and Finnmark up in the north where we have very few people, and here the uncertainty is very big, and this 1.83 is probably wrong. I'll come back to this in a minute. Now, what is interesting is to look to how the lockdown has reduced the reproduction number. In Oslo, the reduction was about 78% at the lockdown, and when we reopened, we lost a lot, just a few percentage points, not much, not many. It has kept low after reopening also. And then I show you here how the prevalence of the hospital prevalence fitted to the yellow data. It was quite fine. You see the confidence bands. Here is how we predicted the next 3 weeks, and here is the truth in the next 3 weeks. So that went fine. And if we look to other areas of Norway where the numbers are smaller, so if I go back here, we had 100 in Oslo, that was the highest number. And now we go down here to 20 in Trøndelag and 12 in Troms and Finnmark. You see that the uncertainty are bigger, and in particular, we start to get strange increases of uncertainty in counties where there are very, very few cases, which makes this, which come from the fact that the reproduction number is estimated to be up to 1.85, as I showed you, right? This is the prevalence map estimated on the 31st of May at municipal level, 356 municipalities. Most is yellow. Yellow means here that there's no virus present in that municipality. Norway was and is still quite empty. If I look to the national picture, by simply running all the counties using the different data, but assuming that the probabilities of transmissions are the same in every county, then we get these numbers here, and the fit is good and the predictions work fine. Again, I can look to the reduction in the reproduction number given by the lockdown. At national level, it was 84%, and then the reduction after lifting the lockdown was 75% compared to before. And these are numbers that compare well to other countries. For example, in Germany, where a stricter contact ban and a stricter lockdown was introduced than in Norway, but comparable. The reduction was 79%. So this is somehow probably a level that can be assumed as confirmed. Here you see the total prevalence. So prevalence of the disease is also an output of our models, of course. And you see here how that in Norway we assume to have roughly up to 40,000 individuals who have been infected until the 31st of May. This is 23, because 8,400 have been lab confirmed. It means that the fraction of confirmed is 20%, 23%. In Oslo, we estimated between 7,000 and 10,000 with a 31% of coverage. Now, very recently, the first seroprevalence studies have been released in Norway. They are small and they have some, maybe I would say up to 4,000 or 5,000 individuals in their study. But they confirm that antibodies are present in about 1% of the population, 0.7% to 1.4 probably, let's say 1%. And this means that 1% means 54,000 people in Norway and 7,000 for Oslo, which is not too bad compared to our estimates. What about the amplification factor? The amplification factor tells us something of how many imported cases were not detected, and we estimate this to be not too much. So 60% roughly of the imported cases were detected, between 40 and 90% in the credibility interval, which is good. If we can increase this even a bit further, we might. This is important for the next importation round, which will come soon, because 100,000 Norwegians are on vacation in the rest of Europe. I compare briefly the regional model with a national model by looking to predictions made from the 10th of April for the next 3 weeks to find out if we are able to understand better when the incidents, the regional incidents, and I look to the percentage of weeks when observed incidence is within the 95% prediction interval. And I call this coverage, and here you see the results. So the coverage is a bit better with the regional model, and there's also something called the energy score from Gniting and other that says something on the prediction in probabilistic models that is quite, it's nice to be small, and it's half of the other one. Here you see two maps. These are the municipalities, and these are how the prediction in that 3 weeks fitted to the data. Blue is good and red is not good. And you see that the regional model is more blue than the national model, but not dramatically more, but a bit better. It's still like this, that the coverage in a 95% credibility interval should be 95%, but it's still much lower. So we know it means that we're having either more or different transmissibility within the county. There is a clear distinction between urban areas and rural areas, and some of these counties have both, and probably transmission is different there. Possibly there is a problem with the mobility that is wrongly estimated with the Telenor matrices, because we lose some information there. The seeding could be maybe not good enough. It's geographically more heterogeneous, and there might be missing covariates. Long-term predictions, I'll jump over them. We do long-term predictions for the next year by running these 1,000 particle sets further. And you see that in Oslo, it means that this is incidence, so we have seen the peak so far. But when we go to the regions that we are not estimating well, so here this is hospitalization in Troms and Finnmark again. I showed you before the uncertainty here in our predictions, and here you see that the uncertainty is showing up as a big peak in October 2000. October, November, December 2020. That comes from the fact that our estimates of the R0 is highly it has a probability of being highly larger than 1. This is a small peak seen so far, but this shows that this result is not very interesting and not very good, right? Nordland is another case, also another region up in the north where we are not doing good estimates. Hospital prevalence, this has been important. Here you see for Oslo, our prediction for the next year have been used and are used all the time to order hospital equipment. And there they simply sum up the number of beds occupied in the next year and find out that it will be roughly 100,000, and they buy masks accordingly. But in Troms and Finnmark, our estimates are not good. Here we are come up to 1,000 people in hospitalization. Here we are coming up to 100, right? I go back a second to show you, or maybe I jump over this. So this was just to show you that in the phase when we had less data, our predictions were not too bad. Here you see our confidence bands and the truth. But this is how the picture was in the hard moments for Norway when there were not many yellow municipalities, but again in the north here and in Nordland again. So we have working with change points so far. So here you see the 3 change points, the 3 change points, and because we add one on the 11th of May, and we get good estimates. So the current which one is it now? It's covered here. I think it's this one here. So this is the posterior marginal distribution of this probability of transmission here, and it goes up to 1.1 and things like this. But we want to move to a daily varying reproduction number. So a daily varying beta T F for every fylke, or maybe national wise. Now, the reason is that the sequence and combinations of interventions that were really complicated, right, up with one, down with another one, and slow opening again. So all these things, they lead to a time-varying reproduction number, which can change both abruptly, but also very smoothly. And being able to estimate these changes as rapidly as possible is, as you know, very important also for the next so-called next phases. In practice also, this means that we stop to decide when to put change points, right? Which is on the long run, something that we don't want to continue to do. Now we can look carefully and identify why the 11th of May, because that's when the last opening happened, right? But it will be more and more difficult. And in particular, if we start to have change points that are different from region to regions, this is not going to work. On the other hand, we have to remember that in any case, the data that we use have an inherent delay. So it will be in any case difficult to say something on the beta T today, right? And we can easily introduce the beta TF in our SEIR model. We can do some ABC also, sequential ABC, but it doesn't scale up very much. And we have to start using splines to model the beta T if we want to use the sequential ABC. And the MCMC doesn't work because it's stuck, as you know. Therefore, we move to a sequential Monte Carlo particle filter. And this is using work from Andrieu and colleagues and Geir Storvik, and very rapidly. So this is work still in progress. So we keep the beta T, this is now national beta T, the beta T constant until the March 6th. And then we let it change every day. We assume a random walk prior on the log scale of beta T. So log beta T resembles log beta T minus 1. We use a binomial likelihood for the number of new daily hospitalizations. And we compute the likelihood by sequential simulation. We have a recursive formulation for the posterior that you need to do the particle filter. We do particle resampling as needed, and we do some smoothing very rapidly. But this is what comes out. I have 1 more minute, right, jumping, or maybe
even
not.
2. But
even 2
questions.
But then we're done. So here you see the estimate of the daily varying RT with a 95% confidence band. This first red line is the lockdown. The RT collapsed very rapidly. It remains here. Then here is the reopening. In the reopening it goes up, it touches 1. For some reason it goes down again. And we see these, you see these cycles. We don't like them so much. We don't understand them so much. We see that also. If I look to, so this is today or a couple of days ago. If I go back 2 weeks, this is somehow the last day that has been really informed by data. Here the data becomes poorer and poorer and poorer. Today there's nothing that informs the BT today. We use hospitalizations. So you see the enormous confidence interval here. I mean, 2 weeks ago, it was okay. It was comparable to the change point one that we have. And just for a comparison, you all know EPI-ESTIM that uses percentage positive tests in Imperial College, Oxford, and you see here, also here, more or less the same uncertainty of in the confidence bands, and also here you see oscillations. So maybe they are there. Just a word on prediction. So if we want to predict the hospitalization the next 3 weeks, which probability of transmission should I use? Well, in the change point model, we use simply the last probability of transmission estimated with the confidence interval, here it is, and just sample from there the future, right? And if we are using the sequential one, well, we can't trust this last one, of course, right? So which one do we use? Currently, we are making a suboptimal choice. We're using the distribution that we find here 2 weeks ago. But I would be very interested to see other suggestions, new thoughts that you might have. And finally, to conclude, there are many useful and good models. This is not the only one. Inference is difficult because the data is really poor, and it's small data sets in this world of big data. And the system that we are modeling is complicated, has lots of parameters, and the model is available only by simulation, right? Which is time demanding. Some hypotheses are difficult to justify. We find that mobility is important early in the epidemics when it matters how it spreads in the country. It's again important now because Norway is empty, there is very little virus here. The regional scale is useful, but again, there are some regions which are not, where we don't have good results. And finally, I haven't mentioned this very much, but the confidence intervals or the credibility intervals are very huge, but still they carry important information for decision making, and that's what is important. Thank you very much, Jampi.
Thank you very much for this talk. There have been some questions. I would like to remind those that are with us that they can post questions using Slido, and if they haven't seen it yet, but some have, the code is in the chat of this webinar for writing questions to Slido. And now there are some questions already. I don't know if Arnoldo can see them somewhere, but I will read them anyway, because I see them.
I can't see them, I think.
Okay, Claudio Struckiner from Brazil started by asking, is there any way to estimate the number of contacts with the NOR's data? I mean the number of cell phones in close contact with an index phone. How many?
No, so the data that we have does not allow this, Claudio. So because it is only total counts of movements between one municipality and the other. So and the reason why we got those data is that they are completely safe from a privacy point of view. They can be published. They are not, there's nothing, it's impossible to go back to individuals, right? What you're asking for is these things that have to do with Bluetooth and or GPS, and the data that are connected by those apps are of course very interesting, and they say something on the contacts between people. Haven't seen these data used yet, but they will come, and they will be important, absolutely.
Claudio had a second question, which is, I wonder about the implications of accounting for heterogeneity, such as super spreaders, population density differences, I guess, occupation of people. Yeah.
So the modeling group, we have an agent-based model that is running also, but in the model that I presented today, we have no age and no occupation and no super spreaders in there. So you can do it, right? You can start to introduce new compartments and it's feasible, right? But all this means that you have to introduce new parameters, and some of these parameters are very difficult impossible to estimate, and very difficult to get to know from other literatures or other studies. So you will start to make assumptions that are really hypotheses, as I was mentioning, that are really weakly founded, and so yes, you will get stronger results, but how safe they are, it's more questionable. So we have decided not to go in this direction so far, because we see that we can't inform our models in a safe way. But technically, it's possible.
Now for a question from Peter Trappman from Stockholm, almost a neighbor. Are travelers chosen at random from the population, or do people traveling from Oslo to Bergen, for instance, on Monday, more likely to do the same on Wednesday? So are there subgroups who travel and do all the traveling, or do everybody mix?
No, so the data itself has no information about this, right? So it just counts every 6 hours who moves from where, but it doesn't track any person over from 1 6 hour to the next. As I was mentioning, we try to do some tracking within the short time, in a short time frame. So if I move to Bergen, And Telenor tells me that after 6 hours or after 12 hours, some people from Bergen has to be sent back to Oslo. Because I'm an Oslo resident, I will have a high chance to be sent back to Oslo than a guy from Drammen or from Trondheim. This can also happen, but because there is randomness, we always choose at random. But we favor a return to the municipality of residence.
May I just put in the thing? Is there no data you can compare with from, say, the National Statistical Office, where they probably ask about who commutes and who does not commute, and do the numbers correspond in any way? Have you looked at this?
No, they don't. And that is interesting. So when we started the project, Jumpy, we had the commuting estimates from the national office, which is based on surveys made every year, or I think something like that. And we could use them, of course, but we think that of course the COVID-19 situation has changed the movements dramatically, and so in fact those commuting is not appropriate. While the mobile phone data movements, they are real-time movements, and they adapt very clearly to the actual movements, and we saw it in the data. So I think that it was important to use the real-time movement and not the more static ones that were available.
Peter has sorry, another question. You take into account clusters of hospitalizations through outbreak in care homes, for instance, if you have had this, which might explain peaks in hospitalization, but not in R0.
No, we have not done this, but this is an interesting suggestion, Peter. I like this. We have had some clusters that were recognized that has led to hospitalizations, and we were not modeling them so far. But it is, and in particular, this can become more interesting in the future when, if it is like this, that we will mainly suffer from local clusters, then this will be more important.
Yes, that will be a problem for the definition of R0 in a way.
Correct.
What R0 will mean if you just have...
So we can start to do betas, probabilities of transmissions that are that take into account clusters and things, and we might need to do it. But again, what is important for us has been to make predictions of hospitalizations, right? And maybe predictions, there are things that compensate a bit. So maybe it's not so dramatic to assume independence.
Now, I was also wondering if it would be interesting to fit this model to some other country with more cases to see if it works anyway, or if it works well, because there is this decreasing trend in Norway, and then it keeps very low. And if it keeps very low, that's easy to predict. And then you can always say, I don't know about the future. And could you?
So we would very much like to try it on any other countries. So we have not seen these mobility data used in other places. We start to see now some Google data, but which maybe is interesting, but we haven't seen mobile phone mobility data at regional level, at municipality levels used in other countries. But you are right, Jumpy. So when there are very, very few cases, R0 doesn't mean anything, right? In itself, and we are in this situation now. Even at the point that we have stopped to report R0s in our daily reports because it's misinterpreted now. We only show predictions, and so yes, I would like to try it out in a country that has more COVID-19.
Well, because R0 would be heterogeneous in itself. I mean,
Yeah.
it could be high in an old people's home and then
Yeah.
very low around it or something like that. And then that would be difficult, or high in a school class, but not in their homes or whatever.
Whatever, yeah. We have to think that agent-based models are also better to answer some of these questions, right, than compartment models.
Yes, no. One question that I always have with movement models is whether people who move behave like the locals or not.
Good question.
Do they have the same contact pattern? Should you really count them in as locals for a couple of hours and then out again, or do they have? But that of course is another kind of survey.
Yeah, we are using them in our model. I mean, everybody who is in the municipality, they mix randomly, right? But yes, I mean, don't you think that they will probably move more?
I don't know.
More contacts?
I don't know. I'm thinking about my own travels. I mean, airport, hotel, conference, airport, and back. I didn't mix very much with local population. I mixed with the people at the conference, and those were not local. But of course, I have a strange kind of.
Yeah.
And you also.
But people probably. If you think to commuting, right? They go and then they mix with the people that work there, and then they go home. So I mean, this is an important. I mean, I think we have to be a bit. I mean, the question is, are these complications useful or not? For example, I mean, the mobility data that I've shown you now, right? They give us a little bit a better picture. But not dramatic, right?
Did you try a simple contact matrix between regions?
Yeah, so
that was fixed.
We tried to run a simulation where we use the Telenor mobility data, the real ones, and we tried to run one where we used just a normal week of mobility of Telenor, which is really the first week we have in February. So we use that week all the time in the future, and there is a difference, but not very big. So we have to be a bit careful that. So what do we want? What do we want to do with these models, right? And what complications are useful?
Yes, I guess that one should try to find out how to calculate a Kaike criterion or something like that to see if
so we use a little bit, we use this igniting score measure that is something similar to that, right? And and there we see
it improved a little.
It improves very much, right? But if you look to, okay, so how many predictions are better? You go from 65 to 77%, right? I mean, it improves, but nothing dramatic, right? So
yes, I guess that all modelers are facing this same problem right now. How to
jumping just because we are discussing generic questions. I mean, we have been using this hospitalization data, right? Because the percentage of positive tests are difficult to use because this criteria change. Most models use positive tests, percentage of positive tests, and I wonder, has there been any study that has really tried to model the effort of finding the positives that are changing over time in these models? Because we have somehow some understanding of how many tests they had, test capacity, and what criteria were used to admit people to testing, right? We have this log. Can this log be used in modeling? Has it been done?
Not as far as I know. I haven't seen a strict analysis of these. Also because you would probably have to split these numbers into those that are results of, say, some kind of contact tracing, those that are generic workplaces like hospitals where they maybe test the staff all the time, and those that are simply people saying, I would like a test, if that is possible, because in Italy that was not possible for a long time. They were not, you could not just go and say, I would like to have a test done. Yeah. In other places, maybe you can. And so you would at least have to split all the tests into these classes.
Yeah, and has this, but because this is needed if you want to use the percentage of positive tested, right?
No, I understand that. Ideally, that would be the most direct numbers. How many new infected have you found now? That sounds good, right? And that's also how people interpreted these numbers for the first months. I mean, this is the epidemic, the numbers of positives that were found.
But it's still like this, right? I mean, if you take the newspapers, Jumpy, the Corriere Repubblica, they tell you the number of positives every day.
Yes.
And they look to this now, today is 10 more than yesterday's. And okay. But I mean, maybe the testing capacity is completely stable now, and maybe the criteria are stable, and so maybe this makes sense, but it could well be very wrong, right? I remember in the beginning where was not much capacity here, and everybody who was on, I think it was like this, that had been sick, right? You need to have three negative tests or 2 negative tests to be officially recognized as healthy again.
Negative, yes.
So there were very many negative tests that are in these statistics, right? So but I think this is such a generic and obvious problem that I'm sure that there must be a literature that has tried to define a score of intensity with which you look for the
it's difficult because you have both a disease that may be asymptomatic and symptomatic. So whom you discover depends a little bit on this.
That's important.
It's probably different in age classes. And the epidemic has probably traveled differently in age classes during time. As we said, now we believe that young people are starting to mingle and maybe infect each other more than old people. But in the beginning, there were more old people infected for various reasons. And then, of course, keep track of all these strategies of who is tested, really. Because it's very theoretical to believe that this is kind of random testing of the population or something like that. That is very theoretical. Now, maybe we should work on this, try to... But it also depends on the system that the public has devised for registering these events.
Yes.
I mean, hospital doctors don't really have time to sit down and compile complicated questionnaires on the motives. Why did you test this person? And exactly this.
Yes, it's a good question.
So I don't
know if the Norwegian registries have a motivation. They have lots of data, but have they the reason why this guy has been tested as a column on the Excel file? That would be very interesting.
I think that there was in some data I saw once such a column, but it contained very little. I mean, because of symptoms, because of while we would like much more details. I mean, was the contact of another positive or suspected contact?
Yes.
Had been in the Alps.
Yes.
Had been in the Alps is a motivation.
Yes. So, yes, but because we suffer very much of the fact that we have this delay, right? I mean, that we have to wait. I mean, and on the other hand, I don't feel that we can start to use positive percentage of positive tested yet. So we could, of but maybe we are too careful on this, right? But we are.
The risk is that they are too far away from the true trend. In theory, statistics would say that any correlated information that you add should be helpful, but it also ruins your variances. In theory, it improves things, but it might be too much dependent on testing strategies or campaigns or whatever happens in society. No, I guess the best number are the dead ones. At least if you could get the detail on whether they died of the disease or of something just related to the fact. In Italy, for instance, I guess that Norway has also calculated these excess deaths over previous years. And in Italy, many of these numbers were suspected to be people who died of something else. So they were afraid to go to hospital during the crisis of many cases, or they were not direct, they were caused by the epidemic, but not by the disease in a way. But otherwise, excess deaths would be the... But that's of course very delayed. As far as we know, it's at least 3 weeks or 4 weeks delayed,
3, 4, 5 weeks,
compared to the epidemic.
That's even more delayed, right? That's one reason, and also
in Norway it wouldn't help if you have 1 dead per week, then you would have problems doing statistics.
Exactly, it's too few deaths here.
Yes. Let's see if Peter has one thing. I think Iceland kept track where the tests were from symptomatic people or contacts of them or not.
Okay, interesting.
So maybe Iceland.
Yeah, thank you, Peter.
Yes, tack. Are there any other questions from Claudia or Peter, who are the 2 ones that are with us in this little discussion?
It would be nice to discuss with them also. I mean, this is...
You can, if you all join, you decide to join either today's coffee break at 16. You received a newsletter from the Institute, right? You have seen that there are generic coffee talks, tea talks and coffee talks twice a day, open Zoom sessions for everyone.
Okay.
Either this afternoon, or we could say Monday in the morning, you just join.
Yeah, but maybe now the summer is coming, but it would be, I mean, I will try to follow. This program continues also after the summer, right?
But may I suggest that if you want to talk about such a topic, are the dead better than the living or something like that? We could phrase it differently perhaps. Then we can just write to the organizers, Chiara or Megan, or I don't know exactly who writes the letters, and ask them to give it as a theme for a coffee break, for instance, a certain day in advance. So that people interested in this could join in the coffee break, say next week on Monday, Tuesday, or whatever.
Yeah, good.
We could suggest this as a theme, because already several coffee breaks have themes that people decide we will discuss this and that after a webinar or something.
Good.
Okay, let's then close this webinar. Thank you very much, Arnoldo. Thank you very much to those who have been with us all the time.
Yeah.
And see you soon again on this channel. As they say.
Ha det bra.
Ha det.